Okay, welcome everybody. This is our third and last day of Next Generation Electrochemistry 2021. You've seen these slides many times now, so I'm going to go straight into presenting the panel that we're doing this morning. This is again a discussion panel like we've had a few times already. So we go back to the discussion panel format after a break yesterday afternoon. The discussion, a reminder, is driven by the panelists. These are experts in the domain of electrochemistry that we are targeting in this panel. They will all give you a short opening statement, giving ideas on fundamental questions, fundamental topics that have to do with the theme of the panel, with a connection to electrochemistry. And then after that, those of you in the Zoom call will be able to start interacting with our panel. I hope that you'll be as active as you've been all along and asking lots of questions. We are also live on YouTube. If you're on YouTube and would like to post a question, we were able to get to them yesterday, and we'll notice them, and if we can, we'll get to them. We are going to run for 90 minutes, and I'm going to do like with the other panels and then pretty much at 90 minutes to be respectful of everybody's time. To our panelists, we want you to be bold in the way that you present the topic so that the students get a good idea of what is out there for them to explore as they start their career. They're really, really early career scientists. And so if they want to do a career in this domain, what should they be thinking about tackling? We've had some mild controversy in some of the panels, and that is perfect by me. So you can be as thought-provoking as you want, and you can provoke each other if you want as well. You have an opportunity now to send your message beyond your group, and you should embrace it. We have emphasized the idea of thinking critically and making sure that you plan what you're going to research carefully so that you're effective. Attendees, you know the drill. You know there's the 5 steps that I have on the slide. You know how this works. You've done great. So keep doing what you're doing. One quick note that I told the panelists before we started, that even though the official theme of the panel is corrosion, since a lot of you have asked about machine learning, I wanted to note that the 3 people that are our panelists have experience with machine learning. And so you're going to hear about machine learning as well. So if you want, I would encourage you to take the opportunity to ask questions on that front as well. And if that takes us in a different direction than we initially planned, that's completely fine. I want to make sure that you get the most out of the event while we have you here. With that, I am going to relinquish my control. We agreed upon an order before we started, and Santanu Chaudhuri is going to go first. Santanu is at the University of Illinois Chicago like me, and he also has a joint appointment at Argonne National Lab. Santanu, the field is yours, and take it on. You need to unmute yourself.
Hello, all. Hopefully, you're seeing the full scale slide.
We're good.
Okay, good. So, just an introduction and sort of provoking some thoughts, but I wanted to start a little bit back in terms of corrosion panel, right? This is not a traditional electrochemistry panel. So corrosion has a lot of material science and engineering and many other aspects to it. So all the students were coming from different background. I wanted to start with a little bit of a background on corrosion. Because what I gave as my title is Atoms to Grain Scale Modeling of Corrosion and Electrochemistry. And if I were trying to be even more accurate, I should have said electrons to atoms to grains to ions to fluids to liquids, and it will become a long hyphenated list, right? Because corrosion kind of touches all these things. So let's talk about why corrosion is electrochemistry at all. So this is our group, between UI 24 to now, UIUC, then I'm now in UIC and NL. So some folks from Argonne contributed to it, and people who got me into corrosion is from Boeing. As Jordi knows, I came from a lot of people around me were doing batteries, electrochemistry, not in a solid, in a solution phase electrochemistry sense, but in a solid state materials and interfaces and electrodes. But Boeing company asked me the question that, can you model, corrosion? It's electrochemistry. So that got me into this in some way, and they funded us for a while. So some of it is, funded by Boeing, some by FMC Technologies, or oil and gas, some of them funded by ARPA-E, some by Army Research Lab, some by Department of Energy. So why all these people are interested in corrosion? So that's the question I'm trying to get at. So what's a corrosion? So essentially, it's a human endeavor to get metals. I'm talking first about metals, but corrosion kind of touches and has become even broader term than this. So we got all the elements out of, as ores from sulfides, oxides, and we did spend a lot of energy, got them into the shiny new metal. We coated them, we polished them, and we made all stuff out of it. And they all want to go back to where they came from. So they all want to be oxides, sulfides, carbides, nitrates, and whatnot. So this is kind of the thermodynamical process as well. And the kinetics is the rate of corrosion. Sorry, my slide wants to go further. But the step one is chemistry at the metal oxide interface. Then you have grains and grain boundaries from material science. So even the composition as grain boundary changes the potentials of the metals that you have, and then how noble they are and how corrosive they are. And then you have different precipitates that form this anodic and cathodic spaces on a metal surface. And that, then you have different discussion of inhibition kinetics, how you can cover them up with the coating, and how these coupled heterophases are running small batteries on all places on a material interface when they're galvanically coupled. And the metal loss happens. And when metal loss happens, start growing pits, you can start growing cracks, and metals can fail. And as a result, everybody's interested in when will it fail, right? So the corrosion is all about, how can you design better alloys? How can you design better coatings? How can you, predict the material's performance when it's going to fail? So that's where my group comes from as a multi-scale connection. Let's go to that multi-scale connection a little bit longer. So what I mean by multi-scale connection is that this is a usual picture, electrochemistry, you have the substrate, and we worry a lot about this zone, that what's happening to the double layer, what is diffusing, what's not diffusing. So if you look at modeling work, if you're trying to model electrochemistry and materials evolution, it's a very hard problem because it goes all the way from as I said, the electrons at the interface, the solid state, how you make the alloy, how you process the alloy, what precipitates are there, what's happening at the solid liquid interface, what kind of oxide is forming. Is it passivating the surface, or the passivation is not good enough? Maybe something is dissolving and reprecipitating back into the interface. So tremendous number of phenomena also happening in that layer. So the concept of double layer is not that easy, and it is difficult to start with, but then it gets more complicated with solids, gels, forming networks of electrolytes and orders. And then you test corrosion using bias potentials that then tests something. We don't know exactly if it is testing environmental corrosion, but that's what we do. We do polarization curves and measure anodic and cathodic currents, look at corrosion currents to test materials. That's how we certify materials and try to predict that, hey, how long it is going to last. But what if, we then, go to even longer time scale, where there is there can be saturations, there can be precipitation, there can be long-term solute-solvent equilibrium. There is diffusion of all kinds, temperature changes, salt then dries up, there's cycling of, sometimes there is electrolyte when you have something in the environmental condition under electrolyte, and then it dries up and then gets wet again. So this is called cyclic corrosion testing. And you also test it in under salt fog environment. And then that's again another time. How do you predict all this from that? You asked that whether this metal alloy is going to last for a year or it's going to last 30 years. So it's a big time scale, starts with electrons, which is picoseconds, femtosecond time scale, and all the way to years. That's why corrosion is a very challenging electrochemistry problem, and you have to connect the multiple time and length scale. So that's kind of where we come from. We first use ICME kind of methods to talk about solid state, use CalFed approach to talk about precipitates and their stability of the alloy. At the interface, we use density functional theory, molecular dynamics, actually look at electron transfer reactions, either explicitly or calculate work functions to know which surface actually wants to donate the electrons for some of the cathodic reactions. And then, we go to, all of this other methods that looks at uncertainty of lifetime evaluation and couple all that thing in multi-scale tools. That's where AI comes in, and it's kind of important. But I'll leave you with one last example of why corrosion is electrochemistry. So let's say that in an aluminum alloy, you have a theta phase, which is the aluminum copper phase, right? So this blue part, it's a schematic, is the alloy. And you have the solution here where this cathodic phase is dissolving and pit is forming, and aluminum is going to solutions. So you can imagine that you have to solve all these reactions happening in the solution phase, and protonation, deprotonation. What is cathodic phase doing? As soon as there is oxygen, you have oxygen reduction reaction. So it's a 4-electron process, and it produces OH minus. Believe it or not, this top of this particle is very alkaline, and this is acidic. And this metal is forming a battery, and you can model that. So that's what corrosion is. I want to give a broader picture of what's corrosion, what's electrochemistry, and I hand it over to Adrien for the next part.
Okay, Santanu, thank you very much. This is a great way of getting started. So our second panelist is Adrien Couet from the University of Wisconsin-Madison. Adrien, the floor is yours.
All right, so hopefully you guys can see the slides, right?
Yep.
Cool. All right. So hi everyone. Thanks, Jordi, for inviting me to this panel. I'm super excited to talk about corrosion. So I'm a professor at Madison. I've been here about 6 years now, and I manage the MAT core laboratory for materials degradation under corrosion and irradiation. And I mostly focus on extreme environments. So irradiation effects, corrosion in high temperature, complex electrolytes. And corrosion is an interesting topic to me because it's really a very difficult one to get into, because you have, as Santanu mentioned, corrosion is material science in the sense often you form an oxide, there is maybe dissolution of elements, so you need to understand how to characterize materials, so electron microscopy and all those kind of things. But at the same time, it's electrochemistry, right? So you need to understand, charges, cathodes, anodes, and currents, and so on. And for some reason, I'm relatively young in the field, but for some reason, I've been with people that have been there for decades, and either from the material science or from the electrochemical side. And I've been in rooms with them at conferences, and I've seen people fighting to the point that people didn't show up the next day, right? They decided to just give up and get out. So because electrochemists and material scientists don't really speak to each other, and corrosion, unfortunately, or maybe fortunately, is a field where they have to talk to each other, right? And so it's kind of cool because right now we're trying to bring the data analytics as part of that as well. So it's another completely different expertise. And so I can't wait to see conferences with data people, material scientist people, electrochemist people. That's going to be interesting. But anyway. So I'm just going to give you here one example on how do we use electrochemistry in extreme environments, and how you need to understand that kind of integrated approach to kind of target corrosion in these problems. So here is just like lots of collaborators. Santanu and Jay are of course part of it. Industries, national labs are interested in the topic of corrosion. So it's really a very important topic scientifically, but also industrially. Just as an example, what I'm going to talk about is molten salt. So molten salt is an example of an extreme environment. It's high temperature, usually around 700 degrees C. It's liquid. There is a lot of ions in there, and the ions they corrode material. If you leave your car on for a year next to the sea, you come back a year after, you're going to see corrosion, right? Because there is this ions in the solution that are going to affect your material. And so molten salt is that, but even worse. So materials in molten salt tend to actually dissolve. They don't form an oxide. It's a little different than regular high temperature corrosion oxidation. You don't form an oxide film. The oxide film is unstable. So you just have dissolution. So how do you use electrochemistry then to understand corrosion? Is relatively simple if you come from an aqueous electrochemical background, in the sense that you can actually do CV scan in the salt to measure the concentration of dissolved ion in the salt. And so if you're familiar with CV scans, here is one that I'm showing, which is done at high temperature, at 700 degrees C in salts, where you just swipe the voltage and you measure your current and you see peaks, and the peaks correspond to some redox reaction that happened in the salt due to the impurities. So for instance, you have chromium that dissolves from the salt, from the alloy to the salt, and you have an electrochemical reaction. Here, you have iron that dissolves into the salt from the alloy, and you have also an electrochemical reaction. So you can basically monitor the concentration of dissolved ions in the salt as a measure of corrosion rate. And then you do that, for instance, for multiple concentration of chromium and iron in the salt to start with, to kind of calibrate your data. And you can correlate the peak intensity, which is the redox peak intensity, to the actual concentration of elements in the salt. So here is just an example of the peak intensity as a function of concentration of chromium in the salt. You find a linear relationship at different temperatures. So then you have a calibrated method to actually measure corrosion using electrochemistry in high temperature systems. So you have a real in situ monitoring method, and that's great. That's excellent. But how do you use that data and make it useful to develop better alloys that resist corrosion? So that's kind of where we started this project with Santanu and Jay, that this is funded by ARPA-E, which is kind of an integrated approach to the problem of corrosion in molten salts. And so the problem is, molten salts, 700 degrees C, you have to be in a glove box, super complex to start the experiment, very complex to analyze the sample afterwards. So you do maybe one experiment in 6 months, one alloy, right? That's not how you accelerate materials design and discovery. So here we are trying to accelerate a little bit the pace. So we use additive manufacturing to create tiny little samples of a given composition. And each one of those samples, then we put a droplet of salt on top of them. So the salt, thanks to the surface tension, stays in the droplet and does not kind of spread out like water would do, and even when it's liquid. So then you have all those this liquid molten salt droplet at high temperature, and then you can, for instance, do corrosion for a few hours or a few days, and then you can see how each material is going to respond to that. And at the moment, what we do is we measure the concentration of alloying elements in the salt afterwards using ICP-MS, which is a spectroscopy technique that allows us to detect how many elements are in the salt at the end of corrosion, and so that tells us how the alloy has performed. And that's great. Then we can use that in a machine learning setting, and Jay may mention that a little bit, but we can talk how we can use the data in a machine learning setting. But the problem is that we don't get in situ data in that case, right? We just get the data at the end of the test. So really, in my last slide here, what I want to just mention is how can we then use electrochemistry in this integrated approach to generate in situ data, and that data that can then really, we can talk about big data at that point, because you get a lot of data in situ. Every 10 minutes you get a scan, and then you can use that data in a actual big data setting. So the idea here is, can we actually measure in the droplets of molten salts, do CV scans to measure in situ the alloying element concentration? And so we develop mini electrodes, as you can see here. So those are about I think 5 millimeter diameter, if I remember correctly. And so this is just a regular 3 electrode, a high temperature setting. It's a quasi-reference electrode, I put it that way. And then we generate CV scans. And of course, then you need to automate the CV scan analysis. So here you have an example of a CV scan that has been automatically fitted with a black curve. You see it's not perfect because it's very hard to automatically fit using electrochemical equations CV scan. There is a lot of things that are going on in there charging currents, multiple redox peaks, and so on. But nevertheless, we are really pushing forward to try to feed the data to automatically extract the concentration of ionic element in the salt. And here is an example of using that mini probe, the evolution of iron in the salt as a function of time. And you see that ICP-MS will only give you the last point. That's it, because it's the end of corrosion. In situ electrochemistry tells you all the story and all the data that can be used to understand the kinetics. So really, here is just to show you very briefly how we can use that kind of electrochemical approach to develop large data sets that then can be used potentially for machine learning to better understand the mechanisms of corrosion. So with this, I'll let Jay mention a little bit about AI and machine learning. So Jay, you can go ahead. Yeah.
All right, thank you, Adrien. So yes, these guys are really well coordinated. So next we have Jason Hattrick-Simpers, who is about to start his appointment at the University of Toronto. He's currently in a transition, just like Nina Balki yesterday. Jason, the floor is yours.
Okay, just to make sure everyone can see my slides.
Yes.
Okay, so the purpose of my talk is a little bit more general. I'm not as much of a corrosion expert as Adrien or Santanu. I wanted to speak a little bit more about AI and what is it actually good for? Absolutely. So let's see, next slide. The way to think about AI or machine learning. So first thing, what's machine learning? What's AI? Machine learning is basically using a set of data or a set of rules to teach a computer to do a task, a prediction, a classification, a regression analysis. It's like a course module. It's something that you can evaluate your students on. AI is the process of a computer having basically human level intelligence. And so if machine learning is the course modules in your bachelor's or PhD program, the AI is the outcome. It's the student who's able to take these concepts and think and create new science. So the way to think about these things is really there's a broad spectrum of tools that are available to you, and they're used in more or less every aspect now of material science. So very commonly in the combinatorial or high throughput field, as in Adrien's project, we do things that look like data analysis and reduction, right? So if you're taking 1,000 diffraction spectra or 1,000 CVs, and you don't want to have to analyze those all point by point in the level of detail that would be required on a graduate student level. That would drive your graduate students crazy. So you use reduction techniques. You use principal components analysis or clustering to identify similar spectra and focus your attention on individual samples. You can use it, Brian DeCoste, who's a NIST with me, was actually using imaging analysis to identify grain boundaries or secondary phase precipitation in steel using neural networks. And so you can generate large sets of features of images and be able to do things like automatically identify and quantify the position, size, spatial relativization of one another for defects. People are using it in STEM and TEM to actually do in situ defect tracking. Kamal Chaudhuri, who is another staff scientist at NIST, actually has this Jarvis DFT, which allows you to make all sorts of different types of predictions about material stability, band structure, number of physical properties just based off of DFT calculations. Likewise, he also does molecular dynamics. There's this whole space of people who are trying to do learned interatomic potentials, because if you do something like molecular dynamics, you need interatomic potentials. But if you're doing complex alloys like high entropy alloys, those interatomic potentials aren't available to begin with. And so generating things that allow you to predict what an interatomic potential is and speed the process of doing molecular dynamics, and just the whole litany, everything that you can think of that you do in material science, from experimental planning to prediction, to data analysis, to noise reduction. These are all things that's inside of the AI toolkit. Specifically from our work, we're really interested in using AI or machine learning to predict new, possibly more fertile fields in material space for us to explore. So this is an example with some folks from Northwestern, Chris Wolverton, Logan Ward, and Apurva Mehta from Slack, where we're just trying to predict something that's hard to describe and hard to predict with DFT, metallic glasses. And so you take large amounts of experimental data, observational data such as there. Let me see if I have a pointer. I do, right? You use those to generate training sets. You create features. You describe what a metallic glass is using physiochemical theories to generate attributes. You then build machine learning models on your training set, generate a set of predictions, and this set of predictions spans now all of composition space, and it's up to you to decide which systems you want to look at, validate or invalidate the models. For the AI, it's all the same. Good data is bad data, good data is good data, bad data is good data too, because it makes the model that much more predictive across all other types of materials. Right? And then you also discover new things. In the case of metallic glasses, we actually revalidate this model from Kevin Laws at the University of New South Wales that says that it's not just atomic packing fraction, but it also has a lot to do with the electron concentration of the atoms. So the really cool thing about this is it just opens up space for you. All of a sudden you have this model that gives you confidence that you can look into new spaces that you wouldn't ordinarily look at. And so really recently, working again with the same set of people, we discovered a brand new metallic glass system that has both wear resistance and hardnesses that are on par with diamond-like carbon coatings. And the really interesting thing about this to me is that this was a system that other people had looked at, but being conservative material scientists, we all look where someone else had a fantastic hit. We look in the immediate area and then we give up the search. We found the best glass formers to be up here. And in fact, this is the area where the materials had the most superior properties and were the most stable to thermal cycling. And so this is basically from a model generated from a bunch of data points in a book to a set of experiments to a patent. I wanted to sort of close discussing a little bit this perspective that we wrote, sort of scientific AI and material science. So there's this general sense among the community that AI tools are good, but they tend to be of sort of statistical nature, right? They're basically statistical models. And so when we live in this very large material search space that we live in of composition and processing, and what is the solution temperature, and what are the concentrations of the multiple potential corrosive ions, the number of experiments that you have to do, random search becomes better than most AIs. Once your dimensional search gets to around 6 to 7 dimensions, random search does better than your standard AI, Gaussian process, or whatever you like. And so the goal is then we should begin to build scientific theories into AI as constraints that will allow us to basically leverage the fact that AI is this infinitely adaptable fitting function that has great interpolative ability, but terrible extrapolative ability. With the scientific laws that we've generated over the past couple of 100 years, which are wonderful in extrapolation, they're not very adaptable. And when you hit the edges of when a particular theory is considered to be relevant, they break, they're brittle. And so you can please look at this paper. In the paper, we identify sort of 4 major areas of opportunity. It's sort of the development of scientific AI, This is a brand new field. You're just starting to see the first couple of papers come out for this. There's the development of the cyber physical infrastructure. So what Adrien and Santanu, well, Santanu is much, computational people have it good. Their infrastructure tends to be pretty well already built. But for experimentalists like Adrien and myself, samples move from place to place. This instrument has proprietary format number 1. Sometimes it's air gapped. Getting the data back together so that each sample has a cohesive history of what's been done to it and what are its properties is a challenge. From the community standpoint, we have a pretty significant problem right now with trust in AI. People have always been skeptical of it, and as more studies come out, people have very excited about the field. There are going to be more and more studies where people are able to point to something and say that didn't work, therefore we should just throw our hands up and not trust AI at all. And so as a community, we have to sort of move forward and identify how can we trust AI and what are the quantitative metrics that allow people to believe what's sort of going on. And then that last bit, right? I'm sorry, I'm sort of running over, Jordi. I'll end in just a moment.
No worries.
That last little bit is partially why you all are here. Workforce development, right? These tools are out there. And any of you probably know by this point that you can download Python, download scikit-learn, GPFlow, TensorFlow is the neural network version. And you can start working on AI and building models on your data now. It's free, it's out there. And in fact, most of the learning materials that we use are also free, openly distributed. You can take courses online and basically get up to a pretty decent level of competence in a couple of months and be ready to roll. The trick is making sure that we understand how the asks of traditional AI type science images, tweets, text, how those things differ from the types of asks and the types of constraints that we have in material science, and then effectively conveying that to the younger generation. And so we sort of identified a bunch of paths forward in terms of attacking each one of these opportunities. And of course, the first one is talking to computer scientists more. Every computer science department in the country has a bioinformaticist, a person who's basically a computer scientist who does bioinformatics, 100% focused on that. Those people don't currently exist in material science. There's no material science informaticist. SUNY Buffalo and Krishna Rajan's department to the side, which is an interesting experiment in itself. We feel like the development of autonomous research platforms, these are AI-driven, either synthesis or characterization or coupled synthesis characterization tools that are able to sort of take this combinatorial paradigm that Adrien discussed and turn it from make 100 samples and see which ones are good to make 100 progressively better samples, all in an automated fashion. Of course, there is going to be a great need for reference data. So people like Santanu are already starting to post their data online and websites with APIs that people can get access to. At NIST, we were very much committed to making sure all of our experimental data and code were available in the open sphere at the moment of publication, so that people can check your results, build on the AIs that you've built, and build something that rolls forward. And this also helps with trust in AI. I'm sorry, I'm going a bit long. So I'm going to cut it off here, and any and all questions I welcome, and thank you all for your attention.
All right, this is perfect. We've covered a lot of ground in a short period of time. We already have questions, but I wanted to do a couple of notes before we start with the questions. Jason, do you mind posting the link to the paper on the chat? That way they can all click, and otherwise they have to kind of copy the address from your slide. That if it's on the chat, then you can just click on it, because I think that that's going to be a very useful paper for this crowd. And so officially, I'm going to open it too, and I'm going to read it because I'm interested in this area too. The other thing that I would say to the attendees is that you've heard of a couple of different ways that, you can classify what Adrien and Jason have given you in kind of a bit of like two buckets, and Jason at the end kind of brought them back together. Generating a ton of data and making sense of it is one place where AI is becoming very prominent, and primarily it's because there really is no choice. As somebody who generates a lot of data as well, you can't do it manually. You can't do it, data point by data point, Excel sheet by Excel sheet. So there's basically no choice in there. You heard that yesterday as well. Data analytics is a big challenge in a lot of the things that are coming in electrochemistry because we're getting more and more complex information. And then there's the aspect that Jason incorporated, which is using all the data that you might have available and using AI there to become predictive. And I love, Jason, how you differentiated between interpolating and extrapolating. That AI is really good at interpolating and not as good as extrapolating, because that's a really good, good framework. I hadn't thought of it that way, and it was very instructive when you were explaining it. So that's the aspects that I want you to take away, as a general bird's eye view of these two. So with that said, we already have a couple of questions, and it seems like the first one was already endorsed by two of our panelists, so it seems like it was a good choice. So Rebecca, take it on. I mean, you had a few questions, so we can, work our way through them.
Yeah, it was really just two related questions that I've played around a little bit with machine learning with like k-means, and it was easy to get our experimental results to cluster, but then especially, this is kind of a naive question, but how do you go from that pattern recognition and clustering that really doesn't have, at least for an experimentalist, any real parameters? It doesn't cluster along an X and a Y and label them, oh, this is how I'm organizing your results. How do you go from that to assign real parameters like known theory and then extrapolate to unknown materials and characteristics of materials?
Okay, I suppose that's my question to answer. So generally speaking, I think of clustering as a means to an end. I don't think of clustering typically as something that's going to give me a prediction. I personally use hyperspectral clustering or hierarchical clustering when I have a ton of data. I don't want to look at every diffraction pattern, but I have a suspicion that there are underlying commonalities between diffraction patterns. And so the clustering in that instance for me is used to sort of push the patterns apart and identify, this is going to be something that looks like BCC iron. This is something that's going to look like a BCC and a B2. And this is purely B2 in an ideal world. It never actually works out like that, but at least starting off with, I can pull things out in cluster, and then I can sort of identify archetypes from each one of the clusters for deeper analysis. If I were to be looking to do predictions, I would have a sufficient description of my materials, whatever that is. Full disclosure, we use largely the MapMiner/Magpie descriptions of materials. In some of the projects with Adrien and with Dan Thoma, we generate some more specialized descriptors of the materials that are often, we find, more predictive. But then I would use something like k-nearest neighbors or random forest classification, because what those will do is they're supervised techniques. You will generate a model from that, and you can then use that model on a set of new possible materials that have been rendered in your descriptor space to generate predictions. Was that helpful, Rebecca?
Yeah. I guess I'm still wondering though, once you have those clusters, even if you're able to extrapolate how do you go about tying them into known chemical theory?
One of the aspects in there, just to get them as an example of the project that we had together is, if you do like the random forest, for instance, classification, there are ways to see which parameters within your input space has actually, more influence in terms of classification or clustering, right? And it's not going to tell you, oh yeah, this is going to evolve this way, and if I change this composition, it's going to go that direction. It doesn't tell you that necessarily, but it tells you, okay, that parameter here is really one that is actually helping a lot classifying the data in different clusters. And that may be a parameter that you didn't really expect. And then now you're like, okay, so that parameter here is interesting. For instance, just to be a little bit more specific, composition, of course, affects corrosion, right? That's clear. But then maybe not just composition. Maybe if you think of sacrificial corrosion, it's not just one composition that is affecting the results. It's actually how the composition evolves as function of the other ones, because there is a protection mechanism between one element toward the other. And actually, the random forest regressor that we used was able to show us that actually it's a ratio of composition and not the composition itself that was able to give a relatively good prediction. So to answer your question, I think it's not like you're going to get everything written as an output, like, okay, this is how this thing is going to evolve as a linear, exponential, or whatever. But you may have some hints on which parameters matter more than others, at least at the level that we are using it here.
I'm going to interject here because this brings an important question that it's a very common pitfall in science in general. If I interpret correctly what you're describing, when you're discovering these kind of parameters, what you're discovering, at least at first, is a correlation, right? You still don't know if that parameter just happened to correlate as opposed to being a parameter that mechanistically defines that behavior. Am I framing this correctly, or can you go deeper than that?
Let me try another version of it, so Adrien can help me out as well. So the way I describe this worldview is that it's a five-step process. So first, measurements yields data, some form of data. Data, when we're measuring, it's unbiased. We have it can have some distribution, or it can have some structure hidden in it, right? So it's called aleatoric and epistemic, and all those terms are aside, but it can have a distribution and structures. Distributions and structures provide some form of inferred models. So this is step 3. So when you have that, it can give you some form of inferred models. So this is called, you can call it hypothesis generation stage. So that's the third stage. Then you go to the fourth stage, then you say that, okay, models permit prediction. So that's the fourth step, right? So then you're saying that, oh, if I have models, it permits me to predict something. So what you then do is that you test, Karl Popper's falsifiability prediction. If I cannot prove with what I know that this model is wrong, then this model must be correct. It's not exactly a true statement, but this is a falsifiability test of a model. So model permits prediction. And, the fifth step is prediction in some sense reflects understanding. So you're getting deeper and deeper into theory, right? So we did science the other way for last 200 years. We did from the 5 to 1. Now we're trying to do 1 to 5, right, Rebecca? So the question you are asking is a big philosophical flip you are trying to do in your world. And flipping this world is not easy, right? Because we started with some theory that was taught by our professors in our textbooks, and this theory should be reflected in the real world. But then you start with data structures should talk to, you do models, and then, this model is supposed to represent the understanding you were taught, right? So this 1 to 5 versus 5 to 1 is the dichotomy that AI is trying to solve. And what Jason was trying to say and what Adrien is trying to say is, we have some science that we know it's a best guess at this point to how to make the stick science as a constraint for AI models. But it's not clean, and it's not going to be clean for a while. But that's what we need, more and more people and inputs to how to make it better.
The way that I would close that would be to think about the fact that being able to predict materials in the end, you might not care if you have a mechanistic understanding if you get the answer that you need, right? And
For
so there's
people,
nothing
yes.
wrong with not having the mechanistic understanding unless you pretend that you do. And that's where the problem of correlation versus causation can become a pitfall. So so that's I wanted to call that out, because there's a lot of papers out there in all these spaces that will basically discover a new correlation, which is useful, which can allow you to find new materials. And this is what this field is really doing very well right now, is say, hey, why do we have to get to the bottom of absolutely everything here? Here's a new space that where you can discover useful materials, right? And do we have all the answers of why exactly these are the materials that we should be looking at? Well, not yet, but we can worry about that later. Here, ultimately, here's your product, right? The problem becomes when you then try to publish that and say, and we know that, because this parameter is important, you build a cartoon of the mechanism and you pretend that that's true. That's one step too far. Right? And that's where if you want to do that, then you have to take step 5 that Santanu just gave you. And so that's where I would, the three of you can disagree with me if I'm not saying this correctly, but.
No, this is good. At the end of the day, what you're going to have to do is to verify your prediction, right? So as you just mentioned, you don't necessarily understand the mechanisms, but you're going to have to actually verify that composition that you predicted is actually great, right?
Yeah.
So you can't just say, oh yeah, if I do this, that's going to work. That's not enough, right? I think, as Jay mentioned, there is a lot of trust issue with AI or machine learning in general. And I saw that there was a little comment here on the publication using AI and how machine learning and how do you assess the quality of the paper, and I think that's definitely a very interesting topic in itself. But nothing beats the fact that at the end, if you can verify your prediction, then people will be like, okay, that's real solid work, right? But if you don't do that step, there's always going to be a little bit of a questioning.
And Jason touched on that as well, because as an experimentalist, you can use these correlations that you can find in these parameter spaces to guide what experiment you do to study the mechanism. It allows you to choose, well, if this parameter is important, what experiment can I do to see if this is a mechanistic important or if it just happens to correlate? So that's another angle that you can bring from this if you're interested in these topics. Rebecca, did you had a couple, more than one question? Did we get to everything? Are you still there, Rebecca?
We destroyed her internet with the answer.
She still appears to be there. I'll follow up in a couple of minutes in case she's having trouble.
It happens sometime.
So we just grazed your question, but why don't you get the floor and ask it, and that way we can just have a complete discussion.
Yeah, I really like just what you all try to describe how the process works. This is really helpful from an experimentalist point of view. And I only have a very little experience on the clustering side, the k-mean. So just I kind of know a little bit how it works, but I'm asking the question more from the user end, like if I want to look for a library on the Python or GitHub, or a lot of people share their code and their method. And also on the publication, there are so many options out there. Almost you need to write another library to help us to know which one to choose. So yeah, I'm just curious how, like for example, for the publication, how were the paper being evaluated? Not just aside from the scientific question side, that's probably the first criteria, but on top of that, how technically it was evaluated. If I, for example, I have a specific need and I want to look for a tool that is available because I'm not a coding person, right? So how do I know which one is the good one for me? What should I be looking for?
Okay, that did seem like two questions. Let me attack the first one first. I guess sort of what I start with, open source platforms with a GUI are what I like as an experimentalist. There's Weka, which is a Java-based AI platform. Let me see if I can pull it up and pop that into, yeah, I found the Wikipedia page. So I'm throwing that into the chat now. It's Java, it's open source. You can get down into the code if you want. You can do coding as well. But what it allows you to do is import your data frame and then just try out for yourself a whole lot of different pre-processing, classification, and regression tasks, and sort of get an idea for, there's no one-size-fits-all algorithm that you can just implement into any one of your projects. Some tasks you can identify, this is a classification task. I'm looking for a yes or a no. It was corrosion resistant or it was not. Some are clearly regression tasks where you're trying to fit some sort of a function and you want a value out. And that'll help you sort of knock out one of the two primary groups of data, of algorithms. But then it's really a lot of the time you're going to spend time just digging around, trying out different algorithms. And something like Weka is very helpful for that. Things that are very powerful, people use random forest a lot, maybe too much. And it can be used both for regression and classification tasks. That's fantastic, Adrien. Scikit-learn, yeah, awesome. But if you're not familiar with coding, that can be a little bit of a jump. Weka gets you right in your GUI, and you even see what hyperparameters you can tune. And it even now has an auto Weka app that allows you to just say, hey, throw everything at this and tell me what performs the best. I hope that's helpful.
Yeah, I mean, all those algorithms are written already, all the basic algorithm. Then, right? So what I think the difference now is all the things that are on top, like the GUI, for instance, and how the data can be analyzed properly for your data, for your kind of experiment, and that's where like people like Jay, for instance, and all that are extremely helpful. And their expertise is very needed, right? But I understand, as you are new to this field, it can be a little difficult to assess right away, okay, which one I'm going to use, because there's multiple ones, and some are good for the data set you have, some are not, and it's a little difficult to know exactly how to get into this. I didn't know anything about ML 3 years ago, and I still don't know very little. Collaborating with people like Jay, for instance, which is really into it, helped a lot. And going to conferences and all that, and so I would suggest going there by yourself can be a little, traumatizing. So if you can collaborate with someone that has expertise and is willing to spend the time a little bit, or if you if you can attend conference, reviewing, and if you look at review papers that are available more and more now, that can help. Yeah.
Any follow-ups from you? You mentioned that you found that helpful. So
yeah, that's a very helpful. Thank you. How about how do you evaluate the publication?
That's harder. And
for context, the topic of publications is a touchy one in this program. It's been pervading, and it's about to explode in our next panel because we have editors from journals presenting to them, and so take it on, but don't be scared to be sincere.
So some of my first metrics are: do I have access to the code? Do I have access to the data? If I do not, then the paper is definitely coming back for major revisions, and the data and the code will be available to me. Otherwise, I don't believe it at all, and I'll reject it. Second part of that is, am I familiar with the particular suite of techniques and featurization that the authors are using? And if I am, then I'm looking for what I consider to be common pitfalls. I'm looking for signs of overfitting. I'm wondering if they've taken into account potential different physical mechanisms being present inside of their data set that are not being appropriately separated out during their cross-validation training. I'm looking to see if they've done hyperparameter tuning, and that's something that you can pick out by looking at their code to identify whether or not, random forest is sort of what we call bathtub optimization. A lot of different sets of hyperparameters will work and it'll give you roughly equivalent models. We've found that impacts your interpretability, particularly when you do feature importances later on. And so I'm looking to see if they've done hyperparameter tuning. I'm more and more interested. I want them to give me the random seed that they use to generate their data, but I'm looking for their models, but I'm looking for robustness of the models to the random seed, because in our material science data sets, we often have very small data sets. And so something like a random forest, which takes a random subsample of both the features and the data to generate each one of the trees, on a small data set can be very sensitive to that. And so you can have values under the ROC curve that look just hideous. I'm generally interested to see that they're generating some sort of statistics around their models so that I have some confidence in their predictions, and a number of other things that just aren't occurring to me off the top of my head.
Santanu and Adrien, how do you go about evaluating machine learning? Because it is something that's a shiny object right now.
Yeah, but I mean, as Jay mentioned, I think the data is critical. Access to the data, right? And it's a whole other aspect of machine learning. Is in general, can we share data? Is it a shareable format? And I think expert reviewers running the code and making sure that the different steps have been followed properly. And I think although I don't like to say that, but for this it's also important. Is also are people that are publishing on this have actually some kind of knowledge about this to start with, right? I don't like usually to do this because it should be, everyone should be given the benefit of the doubt. But for such a hot topic right now where everyone is into it, right? I think it's important to have as part of the publication or as part of the collaborators, people that have actually worked on this for a little while. That helps when you review. They're using a package that is actually meaningful and so on.
Yep. And I will add a small bit to a very different dimensions where we come from is from the computational sciences modeling and use of machine learning. So for example, if you are doing a very hard calculation, so machine learning that we use are used to reduce the computational expense of the work that we are trying to do. So in this case, we have a really heavy computational path by which we can generate a set of answers that is kind of the true north or the ground truth, according to a few different sets of theories. So now if a machine learning paper comes to me that says that, oh, I have reduced the cost of computations by 10x and give you the same accuracy, you would first like to say that, huh, really? You don't have to do all this quantum mechanics. You avoided this, all this. And initially I was very skeptical, but they are winning me over slowly. So I used to reject a lot of paper, asked a lot of questions. But what we are starting to see is that with so many computations and calculations available, electron densities of molecules and fittings, AI is starting to produce high quality correlation consistent basis sets and high quality quantum mechanical solutions. So Alexander Isaev, his papers are pretty instructive that how he has achieved very high degree, especially for molecular cases. Material science, there's a corrosion question. Is there a list like that for material science? Material science will take some time because it's harder for many different reasons because variations in what you think your sample is and what you actually measured and what your model is all over the place. So it will take some time in terms of getting this level of accuracy. But in terms of molecular science, it's getting there in accuracy, and papers are getting more and more focused on getting answers which can be checked against other theories, which are maybe much more expensive, but at least you can do some sampling of calculations and see how good are the predictions. So it's getting there. I was very skeptical at the beginning, if you asked me 3-4 years back, but a lot of improvements in the last 3 years.
Okay, we're gonna get a little bit of whiplash because Samuel has a question going back to corrosion. So, and Alessandra had a pylon on it. So Samuel, why don't you ask, and then Alessandra, if you want to chime in at any point, you can just unmute yourself and interrupt.
Yeah, hello.
Right.
Can you hear me?
Yep.
Yes.
Okay, perfect. So I have a question. Yesterday, we were talking about standardized data reporting for batteries, for example. Cell Press released a checklist for their journal. And I'm wondering if there's something similar for corrosion studies.
So I'll start with the fact that it is not very different than any standard electrochemistry or electrocatalysis. I come from that perspective, surface science, electrocatalysis. So if you are trying to measure the rotating disk electrode RDE data, and you use 5 different models of machines, and you're just saying that what was the speed of rotation doesn't always give you the same answer. Who made that electrode will change the answer. But what you can do is that you can make your own checklist about what is introducing the uncertainty into your measurement, right? So this is a method of uncertainty quantification, and AI even touched this field as well. So there is use of AI in uncertainty quantification. Your head will hurt, but there is uncertainty quantification of AI. So it's both ways. The question is asked, can you use AI to quantify uncertainty, or can you quantify the uncertainty in AI? So from Argonne National Lab, we had some big sessions that we organized for AI for Science for Department of Energy road mapping exercise, where we explored both tools and methods. But the same for electrochemistry, right? So in the corrosion, if you are measuring metal loss, you are using a quartz crystal balance to look at what is the total loss. How you wash the sample, how you collect the samples is there. If you're doing ICP-MS, we find that there's a bunch of error bars depending on what element you are measuring. If you don't understand, then you will be, of course, using in a linear model that all my concentrations are equally accurate. Same for if you're doing OJ of imaging, right? Your detector has its own problem and nonlinearities. So the question is, when you're trying to go from both from the uncertainties of your measurement and uncertainties of your experiments and uncertainties of your model, when you put it together, it can blow up. It can be, you might, as Jason said, sometimes you might have taken a random guess. And my point is that you should take some random guess and see how good or bad you are. You should generate. I ask my students, like, yeah, go ahead and make a random guess, make a random model and say that these are the 6 parameters that are good. And I'll give it some random parameters and give a fitting function and write my own function and ask a code to generate a bunch of random variations and fluctuations on those parameters and see how good or bad your model is. Maybe the space itself is not varying so much. It doesn't have so much undulation. There's all kinds of guesses are going to be almost right. Right. So I give you one example. In one of our projects, we suddenly find we're making bioplastics, and we're trying to use that AI can design better bioplastics. And we find that one of the bigger challenges of bioplastics is that, yes, they degrade, but they also degrade because they have very fast water vapor ingress. So water vapor goes in them. That's why they degrade better. So this is a feature is a good and it's bad because you don't want your plastics, if you're wrapping something, to seep liquid all over from inside if you're making a single-use plastics. What we find is that there is a correlation between water vapor transmission rate and tensile strength, right? So we're scratching our head that why these two things, tensile strength, and then versus water vapor transmission rate. AI is from the data of 200 something data points. Is showing, but the actual answer was crystallinity of the polymer. So of course, if you don't know the science, if you don't know what goes into them, what is the degree of crystallinity, can you look at the mesostructures of grains and why water vapor is going in and how crystalline you are, and you will never guess that parameter. So lists, what it goes in your model is always problematic. You should always consider this as an incomplete. And as in electrochemistry, you have various sources of errors. Before doing AI, you should write it down or try to figure it out, read literature, and see that if you can have a statistical model for the uncertainty quantification models. There's some nice methods right now available which are accessible. Codes are written. Can we use that, right? So that's kind of my long answer to or non-answer to your question, that which one there is no standard way to do it, but it's a great question.
Any other thoughts, or Alessandra, do you have a follow-up?
I sort of yes and no. So you did mention that sort of the way that you do your own checklist is by comparing the data to a random system. Is that, am I understanding that properly?
Yeah, no, I mean, I'm trying to say that in some space, there can be so little variation that you could have predicted it using a random model. You didn't need a very physically interpretable, very complex model, and your random predictions would be good in that space because it's kind of linear space and not varying a lot. And in that space, any prediction can be good. But I was not trying to say that as an example, but I was saying that sometimes you have to doubt your model. You have to ask the question that after all this data fitting and exercise, that if your model is equally predictive. For example, in corrosion rate predictions in magnesium alloys, for example, we have seen an error bar as high as 30%, right? So when we are doing very accurate quantum mechanical models of dissolution and all those things, people ask that how accurate are your predictions? I can equally say that, tell me, I will always find an experiment that matches my prediction. That's not the point. The point is understanding the inherent error in the measurements and why those errors are coming in and how you can reduce them to a level where this question is even valid question to ask, right? Because that's where the challenge is in corrosion. There's so much variations depending on how you work, how you measure things, that if for same materials measured in different places is very difficult. Once what we did is that we went back, it's a DOE project, we went back to making ultra pure samples because sometimes corrosion was entirely driven by, impurity centers that are like less than 1% that you don't even know, right? So then if you do the model based on the 99% elements that you have, you may be missing that 1%, below 1% composition space, where iron or something catalyzing water dissociation reactions, right? Maybe it is catalyzing some pathway in corrosion that is corroding the whole sample, but you are trying to build a model using a 99% composition. So you have to still know science. Statistics will not get you there because you don't have that data in your data set. In some sense, you have to know what you're measuring and what your sample is. Sometimes you have to go back to 99.49 purity samples, just like in any science. You go back. So we made aluminum alloys, which are ultra pure, and 5 sample costed us, like Ames Lab made those samples for $200,000. We got 5 samples to test, which are ultra pure metals, and we excluded all impurities. Because one of the measurements is hydrogen evolution reaction. Any of you who know chemistry, hydrogen evolution reaction is a very hard way to measure corrosion, because you can be many other catalytic center, transition metals and others may be causing that hydrogen evolution. So you can correlate corrosion rates, but you should not be. So multiple measurements, what we call multimodal measurements, and multiple theories looking at the same problem is the way to go. Random is another option. It's like, say that after doing all this, it's like, is random model equally good? Yeah, you can ask that question.
I'm going to dig a little deeper on this. There's been some exchanges in the chat on this topic, and I think it's a very interesting one because, just to push you a little harder, what you just described, Santanu, is pretty much the same language that led to the checklist that was shared in the chat. The sense, in electrocatalysis, one of the things that we discussed on Monday is how, small impurities can, what you just said, right? Small impurities can direct your catalysis. Cations that you were adding as your electrolyte turn out to also direct your catalysis. Mm-hmm. So it's, and in the battery space, it's similar. Christine Pearson said on Monday, you add a small amount of an additive, and it turns out that just that small amount that additive coordinates to lithium changes the way that the reactions are happening, the degradation is happening at the interface. Very similar topics. The battery space has a checklist. So they've come up with, there's actually 2 of them, which are both in the chat. So, there's somebody that threw something out there, and I'm actually struck by the fact that corrosion is more ancient as a science. It's been around for longer, and I'm struck by the fact that there doesn't seem to be something like that. So, now that you've seen the checklists, and I can't even follow what the chat is saying, but what are your thoughts on being able to do something like that for corrosion, so that at least if people are going to claim to have discovered the coating that prevents corrosion to eternity, right, how do you check that that's true or not, and not a trick of the way that they did the experiment, which is what happens in the battery space?
Can I just share one slide on this? Go ahead. Yeah. So what you see here is I put it on the chat, is a review paper on corrosion of materials in molten salts for the whole literature the past 30, 40 years. And
would you mind putting it on full screen? So
it's a little bigger? Yeah. So you have it here.
Go ahead.
Can you see it?
Yeah.
So you see it's all over the place, literally all over the place. You have weight loss that are enormous, some that are very benign, and over time that goes from a few hours to hundreds, thousands of hours. And that's a big issue in corrosion, is the fact that all those, this is maybe the same, close to the same alloy, the same salt, the same temperatures, but the big problem, is that the experimental parameters matter a lot. If you think of dissolution, well, dissolution depends on the activity of the dissolved element in the electrolyte. And so if you have a very small cell, that activity is going to go up very quickly, and you're going to reach equilibrium very quickly, and corrosion is going to stop. Impurities, a lot of impurities is important in many electrochemical problems, like molten salt, oxygen, moisture, all that. If you don't report those, and those are very complex to report, very difficult to precisely measure, then it's junk because we can't reproduce your data. And there is a real need in the community, and we talked to the ASTM people a lot. We talk to the National Lab a lot because it's more, I think it's more something that should be put forward by national labs, because this is kind of a global approach. It's not just one lab that should say, hey, let's do that checklist. It should be a concerted effort led by a national lab with experts from universities and other entities. But the problem is, then how do you want to make prediction out of this? This is garbage, right? 30, 40 years of data lost. Tens of hours of 10 millions of hours of very excellent researcher lost because we can't use it. So I just wanted to say that, yes, we need checklists. It is extremely important, especially when we go into systems that are a little bit more complex than just a regular aqueous, simple sulfuric acid or NaCl type of data, right? So, and that's a big problem right now, very big problem. And so what I would really push, I'm sorry if I'm a little long here, but all of you, report your experimental parameters as much as possible, your experimental procedures. It goes to the point that, for us, in every single publication, we report, for instance, the volume of salt that is used, the size of the capsule, the material of the capsule, and so on, right? So being very precise is not a problem. You can even put that in data in brief now that you allow this kind of thing to even be more exhaustive. But it is super important, otherwise your data is unfortunately useless.
Oh, I thought you were going to say something, Santanu. I thought so one thing that I will say is in the battery space, and just for I guess for your reference of how this came to be, this was a bit of a feedback loop. The national labs, so I'm being live streamed, so I don't want to put people on the spot, but I've had conversations with people in the national labs that have the knowledge base all over the US to put it on a checklist like this, perhaps not a checklist, but a paper out that says, we need better benchmark reporting. And what really matters ultimately and what games you can play. That never happened. And there was a bit of, this perception that they don't want to antagonize anybody in the field by, So it ended up being a neutral player in a sense, which were the journals. They're not quite neutral, but they do have a lot of power over, and they are more decoupled from the scientists in the field because there's plenty of scientists that will send the papers, right? And there was a bit of a feedback loop where we were all kind of complaining about it. And in the end, the journals just picked up on that and said, okay, here's a checklist. I don't know how exactly they wrote them, but I can tell you it wasn't National Lab standardizing anything. It was the journals themselves that did the work. Is there an engagement of this sort that perhaps is an opportunity for you to do? What do you think about that? And Jason?
Very good. No, it's a very good point. I didn't think actually too much about it. But journals like Corrosion Science, for instance, which is kind of the most common journal to publish relatively good research in corrosion, that's something that I think, they could definitely put forward. I completely agree with you. That's a very good point.
Yep.
Jason, you had a thought. Go ahead.
Yeah, I just wanted to emphasize that we should do our level best to over-describe and over-report our material systems in our experiments. But particularly when we're dealing with like true experiments, we should be prepared for there to be untracked correlatives or untracked descriptors or features. I was working with a company. We were doing some electrochemistry in 2 locations. They were doing their level best to capture everything possible about their data sets. And we found that at least their electrochemical data between the 2 locations was not comparable. In their design of experiments, scientist A versus scientist B versus scientist C, we're getting very different results, and we still haven't tracked down what the missing feature is.
Yeah, I remember a story like that from when I was a PhD student, and the classical example of that is humidity changes, and not necessarily in the electrochemistry, but humidity changes because the weather is changing from one day to the next. Throwing everything off, right? And not recognizing until you finally have a controlled environment, and then everything becomes reproducible again. We have a few minutes left, and the topic that you mentioned now, Jason, the idea of over-reporting, and Adrien, you said something very similar. Make sure that you share in your paper, all the details of what you did, and all the data, all the raw data. So we talked about data sharing, and I have a note here of something that I wanted to bring up with you, since you've thought about this quite a bit. I know in my group, we generate large data sets, and one of the issues that we encounter is, where do we even put these data sets that we have trouble storing ourselves because we don't have enough storage? We don't have that problem, but we've had to, anticipate that, because some large data sets, and I can see these high throughput experimentations that can build up very quickly. Do you know of resources that our attendees can use that are good repositories to share data with everybody when the data sets start getting unruly, right? Something where the size of the data set becomes the issue of where to put it. Is there something out there that they can use to fulfill those data sharing recommendations?
So
yeah, go ahead, Santanu.
Yeah. So Argonne, we have materials data facility, the MDF, right? And they are offering right now that they will even help you with some effort time to get your data into MDF. Okay. So they're looking for data. So this is the disconnect in the community. So we are in this, Jason, Jay and Adrien know this. There's a MARTA group, and we have work group, and we work with NIST. The people who make tools for data repository, they somehow cannot get data. And the people who make data, they cannot get somehow their data to this repository, right? This is because this middle piece is how to, the databases are made with certain assumptions, format, and APIs need you data to get into, neatly fit into something, right? And then the experimental data is organized in completely different ways. And, mostly in Excel spreadsheets and some in Origin. And in my group, there are like probably 5 different plotting used by my students. I cannot even convince my own students to use a standardized method, right? So I'm not trying to preach here, because I don't have a good track record even in my group, because they're all kind of plotting using their own methods. Somebody using Google tools, somebody using Python codes, data analytics. So, but there are signs of light from these data repository managers. We're also willing to help you, provide you some training, and even provide some. So I would say Blaine Blazik from Argonne, who maintains the materials data facility. I will be happy to make contact with Ben Blazik and Ian Foster's group, that he promised that he will help you. And if they write a paper, they publish a paper, they will also make you a co-author. So you can get a free publication out of it.
Would you mind posting a link to the MDF on the chat so that people have it?
I will.
Yeah, this was a bit of a selfish question, because we've encountered this question before, and we want to be good stewards of data. Right. And so then we went to look, and then like, well, we have this terabyte of data, and now where do we put it, right? Right. So this is very useful. There's also the question of standardizing the data formats, which they may not be thinking about, but we've encountered that one too. Is there a way to go about it? Is there some sort of like write-up or recommendation of how the data should be, saved or classified? I'm thinking,
it's called fair
people that start standard. Now have the opportunity to learn that up front, and then that way they can build a habit, and it's easy to do, right?
Right. So you should, read the paper. I'm just going to put it on the chat. It's called Fair Data Standard. FAIR is an acronym, and that's what we are going after, right? And each of this findable, accessible, these words have meaning. So it's probably better read the paper that just posted on FAIR Guiding Principle for Scientific Data Management and Stewardship. And it can be used in all areas. In fact, at Argonne, we right now have an effort where we are asking everybody's data to be AI ready. And that definition itself took like 9 months to agree on. But I think that we'll soon publish some standards that we sort of agree on. Like, there are a lot of people who don't, but that what we should make our standards, because everybody thinks that we're going to push for a standard and then people have to do a lot of changes to their data and what they do. And there's a lot of resistance that, oh, no, don't push any standards, please, right? So there is two sides to this coin, that if you push a standard, it takes extra effort. People are like, no, the project has ended. I cannot work on that data anymore. It's in a very different format. We can't do anything.
Which is why it's important to do it up front. You start with those habits, and then it's just natural, right?
Yep.
I make it equivalent to the fact that students now need to learn, most of them now need to learn how to code. It's becoming more of a reality. I mean, whether you're doing experimental work or not, it doesn't matter, because coding, data analysis is becoming so complicated that you just have to, right? So if you learn when you start, then you've done all that legwork, and then you don't have to worry about, redoing things, right? So revisiting things is going to be hard, but making sure that everything from now on gets done in this way, I think is perfectly doable. I think that it's just a matter of people, having the will to do it. So I'm hoping that those of you that are here in this discussion will take that on and will find ways to follow these practices, whether, irrespective of what field you're on. The same way that you threw the checklist at them from the battery space, they're throwing at you the importance of sharing your data accurately, so that others can extract other information from it. Okay, so we're at 11:30, and so I want to make sure that we keep everybody's time, we save everybody's time so that they can go on and do the other things that they have to do in their day. So let me thank you, Santanu, Adrien, and Jason, for the time that you spent with us, for all the resources that you're putting on the chat. This is great. I've borrowed a few from my own group. So selfishly, this has been very productive for me as well. It's been a great discussion that's gone in all sorts of directions, and that's perfect. Thank you for your time. To my NGenE attendees, I'll see you in an hour and a half for our publication panel, where you can attack the journals if you want to ask them questions about why they publish what other people do and why they don't publish your papers. The panelists, if you want to join us, you're welcome to. You should have the link as well.